Okay, so welcome to my talk. I'm going to speak about cross, which is a scheme we proposed with this wonderful team. Okay, so in a nutshell, essentially cross is composed of three main ingredients. First of all, we have a new problem, which is something that we call the restricted syndrome decoding problem. And we have also a variant called RSDPG. And essentially, well, first of all, the problem is not really different from non-binary syndrome decoding problem. So I would say we can have a pretty good understanding of the actual security. And also it seems like a really good choice for zero knowledge schemes because you can have very small messages, a fast arithmetic, so it makes sense. Then we have a zero knowledge protocol, obviously. And in particular, we chose a very simple one, which is inspired by the CVE protocol. And I will spend a few words on the protocol, but in any case, we did this choice because it is a good trade-off between signatures and computational complexity. And finally, we have some optimizations. I will not spend time on this because you know all of them. It's like the C3, Merkle trees, the standard ones. Okay, so this is the problem, and this is something that we introduced 3 years ago. And essentially, you can see that the problem is really like the syndrome decoding problem with an additional constraint. So we are given a parity check matrix H, a syndrome S. We want to find a vector X, whose syndrome is S. We have some requirements on the Hamming weight, but also we want the entries of this vector to be restricted, which means that they are either 0 or an element of the subset E. E is what we call the restriction. Since the problem is really similar to syndrome decoding problem, earlier this year we published a paper in which we study solvers for the problem. So we started from ISD, information set decoding. And you can see that, okay, this is an example for rate 1/2, finite field size equal to 251. You can see that essentially the complexity of the problem of the solver depends on Z, so on the size of the restriction. But what is really interesting is that if we consider the SDP case, which is the one when Z is maximum, so Q minus 1, we get an higher complexity coefficient. And the reason for this is that if you think about how ISD operates, essentially any ISD algorithm requires to guess positions of zeros. In this case, when Z is small enough, we can have a maximum Hamming weight and still a unique solution. So there are no zeros, there's nothing you can guess, you just need to enumerate vectors. So the solver becomes slower and the problem is harder. So yeah, in the end, we can have the same security we have with SDP, but using a shorter code. So the code length is smaller. And this is good because obviously the objects become smaller, so everything is faster, etc. Okay, so the problem, I mean, here we are not specifying anything on E, so you can choose any set that you like. For cross, we made a specific choice. So this is the set we are using. So we take some generator G, and then we consider all the powers of this value. We see that this E is a cyclic subgroup of the multiplicative group. Then we set Hamming weight equal to n, so we have maximum Hamming weight. So in the end, the solutions to the problem live in E to the n. That is, the set of all vectors whose elements are powers of G. Okay. Then we specialize further the problem, and we consider the G variant. What we do is that we consider E to the n as a group, where the group operation is the component-wise multiplication, and then we take a subgroup of this group. We do this by selecting m vectors, b1, bm. We use these vectors as a generator set for the subgroup. And so, yeah, essentially what we do is that we consider all possible powers of these vectors, and then we combine them doing the component-wise multiplication, the star operator. Using this restriction, we get the variant, which we call RSDPG. Well, essentially, it's the same as the previous one. The only difference is that the solution should be a vector of G. Obviously, we see that when G is equal to the full group, then this problem is equivalent to RSDP. Okay, I cannot explain all the details here, but I would like to say that essentially everything that we need to do with the group, we can do this very efficiently, like generating elements of the group, testing whether an element is in the group or not, and in the end, we can do everything with some linear algebra. So you see, we have this matrix. This matrix generates all the possible vectors of exponents, and so yeah, we can do all the operations using essentially this matrix. If we compare SDP, RSDP, and RSDPG, we see that first of all, we can have elements which are becoming really short, in the sense that if we want to send these values, the number of bits that we require is getting shorter. You see, for RSDP, we can have n log 2z bits, because essentially we just need to send the exponents. When we consider the variant with the subgroup, to represent an element, we just need to send the coefficients which we use for the linear combination of the rows of this matrix. Since we have m rows, the size is n log z bits. We can also consider transitive maps, which are essential to achieve zero knowledge. And again, if we compare with SDP, we see that the size of the objects is getting smaller, because essentially the maps are the group elements. Finally, if we consider the hardness of the solvers we know about, we see that when we have the RSDP, we can use a code length which is shorter than that of SDP. If we use the G variant, the size is getting even shorter. So, for cross, we used these two problems, RSDP and RSDPG. I don't have time, again, to explain the details about the attacks, but I have some extra slides, so if you have questions, maybe I can give you some more details. In any case, looking at parameters, for all the security categories, we chose the same values for the finite field size, the generators, etc. And you see that these numbers are either Mersenne primes or close to Mersenne primes, because this allows to have a fast arithmetic, so it sounds like a good choice. Speaking about attacks, essentially we consider two types of attacks, so decoding and algebraic. Decoding means ISD. For the RSDP case, we consider the BJMM, and we specify the setting of the algorithm to the case we are considering, because, you know, depending on how you generate the restriction, your algorithm can behave differently, like the number of representations change, etc. And also we consider algebraic attacks, because you can see that essentially we can build a polynomial system such that the solution of this system will be the solution to RSDP. And in this system we are going to have some linear equations, the one coming from the syndrome equation, and also some non-linear equations. These are the ones I call the group equations, because we need to tell the system that we are looking for a restricted vector. And this is easy to do, because if we take any element of the vector power z, this is equal to 1. So this is the system we obtain. And in the end, we found that this approach, solving this system, is much slower than you doing some decoding. So the best attack is ISD. And actually, we received an email by Briod and Oigarden, and they essentially found the same results. And actually, they are pretty good, so I was really happy to receive this email. Okay, now for ISDPG, the situation is kind of different, because the problem is, I would say, a bit different from SDP. So for what concerns decoding attacks, we studied how the knowledge of the group can be used to speed up these attacks. And essentially, you can consider that ISD requires to enumerate vectors. Since we know G, we know the group, we can find pieces of this matrix having a smaller rank, and using these matrices we can speed up the enumeration phase. We took this into account. while for algebraic attacks, we have not been able to find something that works. So right now, this is an open problem. If you want to attack the system, you should look at this probably. Okay. Okay, so finally we can speak about the protocol. And again, I will not give you many details, but this is really a standard protocol, like this is really the CVE plus some optimizations, like sending the hash here, etc. This is a 5-pass protocol. Here in the as a first challenge, we have an element of the multiplicative group. In the second challenge, we have a binary challenge, either 0 or 1. We see that when b is equal to 1, we are sending only a seed. So obviously the size for the second response is much shorter in the second case. So we applied some optimizations to reduce the signature size. Some optimizations are really standard, like using seed trees, hashing all the responses, etc. And also we use fixed weight challenges, which means that the second challenge will be a fixed weight vector, so that for most of the rounds, the verifier is asking for 1, so that we can send a seed. And so this makes the signature size shorter. When we do this, we have to consider forgeries attacks, because for instance, there is this attack by Kales and Zaveruka, where they consider essentially they make use of non-interactivity to speed up forgeries. We generalize this attack considering fixed weight challenges. And yeah, I mean, the protocol, you see, it is really, really simple, really basic. Okay, so I think you are wondering why we use such a very simple protocol, because we saw a lot of talks on MPC, like very much more modern protocol. So why using something so standard, so simple? To show why we make this choice, I can compare with the RBG protocol. So earlier this year we published this paper where we described the problems, and we applied the problem, the RSDP, to the BG protocol. It is something that Bidou and Gabori proposed for the PKP problem, I think. But you can see that starting from PKP, you can easily generalize the protocol to consider RSDP. This is a very rough way to see the BG protocol, but you can consider that every round of the BG protocol is essentially repeating n rounds of this. This is very rough, but it's a good way to make the protocol very easy. When you do this, essentially you are reducing the soundness error, but you are increasing the number of operations you do in every round. So to compare between the RBG protocol and our protocol, I made this figure when you can see the signature size as a function of the number of cross rounds. So essentially 2 points here on the same value of x, I expect it to have more or less the same computational complexity. You can see that when we use cross, we can achieve better trade-offs, because we can have, if we want to use a very small number of rounds, then the signature size is smaller, if you compare with the RBG. So this is the reason why, in the end, we chose to use such a very simple protocol, because we want to stay here. Indeed, if we do a little zoom, you can see that these are our variants for NIST category 1. We have 2 versions, the fast one and the small one. And okay, 2 for RSDP and 2 for RSDP-G. So you see that the number of rounds we are using is really small, something like 240, 250, something like this, because we were really looking for something that can be fast, efficient. In particular, these are the numbers for the instances we proposed for category 1. We see that the signature size is not incredibly short, but I would say it is kind of acceptable. These are the timings, and also consider that these timings are referred to the reference implementation. We are currently working on an optimized implementation. We are expecting something like a good improvement, but don't take these numbers for true, because it's just kind of guessing. And yeah, okay, so these are the numbers for NIST category 1. Some good things that we have, if we consider the G variant, the objects we are sending are really, really small, because in the end representing elements of the group takes less than 2 lambda bits. So sending one element of the group, we need a number of bits which is less than the size of a digest. So I would say this is good. We also have everything is super simple. So probably having a constant time implementation should be super, let's say, easy, not super easy. And yes, this is also, I would like to thank my team for this work, in particular Violetta, Patrick and Sebastian, because they did a wonderful job. This is our website, and thank you.